Logs and log functions. So when we take the inverse of an exponential equation, it becomes a logarithmic equation. So if we follow steps A, B, C, and D, then we're going to notice that it becomes a log. So it says use y instead of f of x. So we have y equals 2x. Then interchange x and y. So we have x equals 2y. Then the operation that allows us to bring y out of the exponent is called a logarithm. So this would be written as y equals the log base 2 of x. And then part D just says to replace f of x, or y with f to the negative 1 of x. So then we have f inverse, which is log base 2 of x. So notice how the base of the exponent became the base in the log. So we had 2, and now it's 2 in the log. And then note that x right here inside the log, or of the log, you could say, is what we call the argument. It's what is being the log of what? Well, the log of the argument. In this case, we have x. Okay, so here you see that I have graphed the exponential function 2 to the x, which we have done before. Now I'm going to graph the inverse. Well, if I were to identify all these points on the graph that you see here, I'd have negative 1, 1/2. I'd have 0, 1. I'd have 1, 2. And then up here I would have 2, 4. So we know that with inverses we can interchange the x and y. So I'm going to plot 1/2 negative 1 I'm going to plot 1, 0, 2, 1, and then 4, 2. Also note that my asymptote for my exponential is horizontal, and now when we reflect it into a log over the y equals x axis, we have a log function that has an asymptote of x equals 0 now. So just like we know with domain and range, domain of my original is all real numbers, negative infinity to infinity. And because we have an asymptote that we never cross, we have 0 to infinity, which means 0 also gets the parenthesis. And then for our log function, those are interchanged. Now the domain has a restriction because we have a vertical asymptote, and our range is all real numbers. Okay, so we are going to go back and forth with logs and exponential forms, because sometimes we can't solve a log, but we could solve it in exponential form or vice versa. So it's really important to note that we know how to convert from one to the other. So if you look up top here, like we just found, log base b of x is the same thing as x equaled b to the y. So the method that I use, the name that I call it, is the popcorn method. And I say popcorn, you'll see in a second it's going to look like a popcorn puff after it's cooked, of course. All right, so we always start at the base. So the first step is we start at the base and we cross the equal sign and go to the solution. So we say 2 to the 3, because remember we're writing it in exponential form now. Hit the equal sign, and then we land at the argument. And looking at this, we know that 2 to the 3rd is 8. So log base 2 of 8 equals 3 isn't something that we just know, but if we convert it into exponential form, we're more familiar with that. Our second one, we're going to have 4 to the 2 equals 16. Now this third one down here at the bottom, there's two logs because whenever you don't see a base like in the middle, it's always understood to be 10. So if you just go and hit the log button on your calculator, it doesn't show a base, so it's understood to always be 10. Just like we don't say like 1x equals 5, we just say x equals 5. So if you don't see if you don't see the base of the log, you know that it's 10. So we have 10 to the 1 equals 10. Okay, so the next one, whenever we have log and a base of e, we call this the natural log, just like we had the natural exponentials. So we don't really write base e at all. It actually changes into a new type of log. So it turns into ln. So anytime you see ln, it's going to have a base of e, and that's it, no other number. So we're going to say, once we see an ln, we know that there's an e right here at the bottom as the base. So e to the 0 equals 1. And our last, we're going to start with a base of 3. 3 to the negative 2 equals 1 over 9. Okay, so now we're going to go from exponential form to log form. Same kind of thing. We're going to popcorn. And we still start at the base. So, but now we just add in the word log before. So log base 10, which I really don't need to write, of 1,000. So that's our argument. Again, notice how we pass the equal sign and then we come back to it right here, equals 3. So then we have 2 log base 2, because the base of the log is the same as the base of the exponent, of 1/2 equals negative 1. All right, now we have e, so I'm going to write ln, and I don't need to write the base of e because it's understood, of 7.389 equals 2. And then our last one, log base 9 of 27 equals 2/3. And when you're writing logs, make sure the base is a subscript so it's smaller and it's lower than your argument, or else it's going to look like 927 as the argument, which then we would assume the base would be 10. So make sure that subscript is written smaller. So now there's some common logs and natural logs that we're going to work with. Okay, so the first note is up here. We know that log base 10, we're just going to assume it's log. Same thing. If you have log base e, we're not going to write it like an log log. We're going to write ln. Understood that the base is e. Now, if down here in this box below, we have 4 logs that don't have the equal sign. And essentially what we're going to do is we're going to put it an equal sign and solve for that x. And we're going to use the same method as we did before. We're going to rewrite it as in exponential form. So we have 2 to the x equals 16. Now these are called common logs, meaning we should be able to know what 2 to the x is. That gives us 16, and that is 4. All right, down here we have 5 to the x equals 1 over 25. So there's 2 ways you can approach this one. You can know that for you to have a base of 5 and it to become a fraction, that it has to be negative. And what makes 5 25 is 2, so x would be negative 2 here. So you could just know that, or you could think of the uniqueness property and change 1 over 25 into 5 to the negative 2. So very similar concepts. And then because the unique property says with the same base, our exponents are equal, we again get x equals -2. All right, now we have an ln. Now, the base is e. The argument in this case is e as well, so don't get that confused. So we write our base of e that we don't see, it's down here, to the x equals e, the argument. Well, what to the x equals the same thing? 1. And then our last one, again, log, no base, so we have 10. 10 I'm going to write equals x here. 10 to the x equals 100. So x equals 2. Okay, so when we graph log functions, like we've seen before, it's important to note that it is the inverse of an exponential function. So whether we're talking about a natural log or the log log, meaning the exponent is base 10, they're going to be inverses of one another. So this box down here are the characteristics of log functions. So very similar but also opposite of our exponentials. They are one-to-one functions. Note here that the domain now has a restriction because we have this asymptote of the y-axis, which is a vertical asymptote. The range is now always all real numbers, and our x-intercept now, not our y, is 1, 0. Okay, so if we wanted to sketch a graph of this, we note that the parent function is y equals log base 3 of x. So we have some transformations here. The first transformation inside with x is going to be left 2. And out here with y is going to be up 5. Now, again, think of it differently with a log. Our left and right are going to affect or impact the vertical asymptote. Okay, so if I were to take that point that we know is usually right here for a parent function, I'm going to shift it. Well, you know what? I'm actually going to draw my vertical asymptote first. So if it's usually at x equals 0 now, it's going to be at x equals -2. So here it is. We know we're never going to cross this line. And the point that's usually here at 1, 0, we're going to shift. It's now going to go left 2 and up 1, 2, 3, 4, 5. So it's going to look like this. So when we talk about our domain, this is where the left shift impacts it. So it's actually -2 to infinity. And our range is -infinity to +infinity. Okay, and the last thing we're going to talk about is finding the domain of a log function. Now, up top on your paper, you don't see it right here, you need to know we cannot take a log of a number that's less than or equal to 0. No 0 and no negatives. So that means our argument can't equal that. It doesn't mean 0 can't be x, because if we, have x plus 1 and I plug in 0, I'm going to get the log of 1, and that's allowed. It just means that after any translations or effects on the x inside that argument, the total or the whole argument can't equal 0 and can't equal a negative number. So we're going to think about it like we did in the last unit. 2x minus 3 has to be greater than 0. So for one like this, we can solve by adding 3, dividing by 2, and we get x is greater than 3 over 2. So that's my domain. Now, inside the second one, we have a quadratic. So we're going to say x squared minus 3x has to be greater than 0. And if I factored this by taking out a GCF, then we're going to note the two values are the x-intercept 0 and 3. So you can use your calculator for this, but I'm going to sketch it out for you. There's a 0 and there's a 0. And it opens up, so it's going to look like this. So now we want to identify every part of it that is greater than 0, not equal to. So that's our domain. So we're going to come from negative infinity to 0, but not including 0. And then we're going to go from 3, not including 3, to infinity. So this next one is a little bit more challenging, and again, you can plug this in your calculator. Make sure you use parentheses for your numerator and your denominator. So this is essentially what we want to figure out. It has to be greater than 0. And when I graph this in my calculator, I have a vertical asymptote at 3, negative 3, and part of my graph is over here, and then part of it intersects at 3 and comes down and does something funky like this. And we're going to learn these types of functions later in the year. Sorry, it's supposed to be more curvy. All right, so again, everything greater than 0 is what my domain is. And this part over here, not included, because it's always going to be less than 0, because there actually is another vertical and horizontal asymptote. So our domain here is actually just negative 3 to 3. And this last one is an absolute value function. And if you graph it, it's going to be a v that hits at 2, but we can't have it include 2. So my domain for this one is going to be negative infinity to 2 combined with 2 to infinity.